Okay, I'll just speak loudly. Okay, thank you very much for the invitation for me to come here. It's a pleasure to be here and see many familiar faces. So I'm going to be talking about something called Hall crystals. And the work that I'll present is done with Sayak Bhattacharjee, who's somewhere in the audience. Oh, there he is. And Julian Mayman, who's a postdoc at Stanford. And Sayak is a student. Okay. So the subject matter is the fractional quantum Hall effect, which you've heard multiple talks on already. And it's defined by the resistivity. That's the defining property of the phenomena. I'm going to be restricting my attention to a subgroup, a subclass of quantum Hall states known as the abelian Laughlin-like states, which have filling fraction 1 over 2k plus 1, where k is an integer. So these states are well described by Laughlin's wave function, shown here, and we've heard quite a lot of that already. There's an alternate low-energy, long wavelength description of the same effects, which is known as the Chern-Simons theory. And for later, and this will come in handy later on because this is the approach that I'll take in this talk. And for later purposes, notation, this contraction epsilon ADA, I'm just going to call ADA, okay? So for when you see that, you'll know what that means. The lowercase represents a fluctuating U1 gauge field that lives in 2 + 1 dimensions, and the uppercase A is some background field that you can think of as the electromagnetic theory, with which we can extract linear response behaviors like the resistivity. So the Hall crystal has been resurrected recently, and it's sort of an interesting thing because it's a coexistence of both the topological order that we know of in the fractional quantum Hall effect and with broken symmetry, and namely in this case, breaking of translational invariance. So the usual quantum Hall state is a liquid, which has translational invariance, say in gallium arsenide and strong perpendicular field. But the Hall crystal is also a quantum Hall state. It has a quantized resistivity, Hall resistivity, but also breaks translational symmetry. So when we talk about broken symmetry, we have to make a distinction between explicit breaking of the symmetry and spontaneously breaking the symmetry. So for instance, explicitly breaking translational symmetry can be arranged by imposing a periodic potential with when the electrons are in a magnetic field. Now, that's not what I would call a Hall crystal. I want to call a Hall crystal a phase in which translational symmetry is broken spontaneously. And that can happen either in the continuum where you have isotropic homogeneous system, or on a lattice where you break translational symmetry beyond that of the underlying lattice on which the electrons are placed. So just a bit of experimental motivation. Recently, there have been several breakthroughs in observing fractional quantum Hall effect in zero applied magnetic field. A representative example is shown here, which shows a bunch of fractions. This is rhombohedral graphene. But the interesting thing that I want to highlight that's relevant to my talk is that there appears to be topological order closely approximate to breaking of translational symmetry in these systems. So for instance, these are compressibility measurements from which you can deduce where the Chern bands are and how they move as a function of magnetic fields. From there, you can assign a pair of numbers to every state. The first number is the Hall conductance in units of E²/h. And the second number is the density, the filling of the lattice. And so you see a bunch of states, for instance, an integer quantum Hall state at filling fraction, at filling 2/3. And the integer quantum Hall state is a non-degenerate ground state. If you have a rational filling like this, there are general principles that say that you must break translational symmetry to observe the integer quantum Hall state. Okay? So for instance, the 2/3 filling must triple the unit cell to have an integer number of electrons per unit cell. But more than that, you see that states that move in the field, this is the so-called strata formula that we heard from Duncan this morning. There are states that move in the field. These are the quantum Hall states. And there are states that do not move. These are charge density waves. So at a high level, what you see is that there are both charge density waves and quantum Hall states, so it becomes possible that you can have the coexistence of both, as you must in certain states like this. Okay, so another example is that that's been received a lot of attention recently is if you look at the 5-layer graphene system, what seems to happen is the potential that you apply by twisting is at the top here with boron nitride, but the bottom does not have the twist. And so the quantum Hall effect is observed further away from where you twist and impose the potential. That seems to suggest that the crystalline potential is at best a weak perturbation. And in this case, if you observe quantum Hall states, even the integer quantum Hall state may be a Hall crystal in the sense that it breaks translational symmetry. And because there's no magnetic field, these are been called anomalous Hall crystals. But what I wanted to do in this talk is to go back to some older stories and think about the Hall crystal, not the anomalous version, and try to understand it better. So there's an ancient work by Bert Halperin. Yeah.
Both these examples had an underlying lattice.
Yeah.
Is there an example for like heterostructures or something?
Well, so here the statement that's being made is that this is the furthest away from the crystalline potential where the quantum Hall effect is seen. And then there was some theoretical modeling of the rhombohedral graphene, which shows that you don't need a crystal to start with, and you can still get it by spontaneous symmetry breaking. But
the 2D electron gas systems.
I'll talk about that. I think one of the take-home messages is that having a weak periodic potential is much better to stabilize such Hall crystal phases than starting in the continuum and trying to see a crystallization transition, and which might be why we've never observed this in, say, gallium arsenide. Okay, but okay, so there's an old paper by Bert Halperin in which he proposed this phase of matter, a Hall crystal, and it's a phase of matter which has, again, quantized Hall conductivity and broken translational symmetry. And the analysis that was done was a study of a Hamiltonian, which is of electrons in a magnetic field, the kinetic energy, plus some 2-body and 4-body potentials, which explicitly break translational symmetry. There's a Q here, which is of the order of the inverse interparticle distance. And when one studies Hamiltonians like this and use Hartree-Fock, you indeed find Hall crystal phases. What we wanted to do, whoops. Yeah, what? Okay.
The second term is a 2-body interaction term?
This one? This is a 4-body. V2 is 2-body, density.
X is actually x1 minus x2.
Yes, this is R is x1 minus x2, that's correct. And this one here has got 4 bodies, yeah. It's not permutation symmetric, but that's what they study. Yeah.
What's the difference between the Hall crystal and the Wigner crystal?
Wigner crystal has 0 Hall conductivity, right?
So thinking in terms of crystalline state.
Yeah.
One kind of crystalline state is the Wigner crystal, and the other one is the Hall crystal.
Yeah.
And so the way that you distinguish between them is that the Hall crystal you still have a measurable Hall conductance despite.
Which is quantized. Yeah. So exactly. Yeah.
Then it went from a Hall system with quasi-particles crystalline.
Yeah, so the question is, suppose you are in a quantum Hall state and you deviate a little bit from the filling fraction, and then you see you nucleate some quasi-holes, say, and they form a Wigner crystal. How is that not? That's a different kind of Hall crystal. That turns out to be different in the sense that if you change the magnetic field further, you increase the number of quasi-holes, and so you can populate more. The lattice is more compressible, whereas the Hall crystal that I'll talk about is a different thing. It's more incompressible.
Motivation of excellent proton mass.
Yes.
That goes to?
In the continuum, yes. Yeah, but as you'll see, we don't have a controlled theory of that, actually. Okay, so what I want to do is talk about an effective long wavelength description of this Hall crystal, rather than in electron coordinates. And I will mostly focus on the case in which the Hall crystal breaks discrete symmetries by you start with a lattice and then you break it further. But it's also interesting to think about Hall crystals from the continuum, as Duncan just said, from Roton condensation. And I put a question mark because I don't think the theory is as on firm a ground as in the lattice case. Okay, so what am I going to do? You start with the Lagrangian of electrons in a strong perpendicular magnetic field with some interactions. And a simple description of the quantum Hall effect is to think about bosons, as we heard this morning, coupled to a Chern-Simons gauge field, little a, and background field, big A. And these bosons are the flux-attached, or if you wish, orbital-attached electrons of this Lagrangian, and their state given by phi. And there's some interacting set of bosons coupled to gauge fields. And this n is an odd integer, so that you can get an odd filling fraction, which is an odd denominator state. Okay, so this is a standard, by now, approach to the fractional quantum Hall effect pioneered by Shuchang Zhang and others. And the nice thing about it is that if you look at this as just some Ginzburg-Landau theory, like we're used to in superfluidity or superconductivity, the phases are tuned by the quadratic term of the boson, right? So if this R is positive, the boson is gapped, you can ignore the matter fields, and then you just have this Chern-Simons theory, it's some Gaussian theory, you can integrate it out. And what you find is that the effective Lagrangian is just 0 plus irrelevant terms. So that describes a vacuum or insulator. On the other hand, when R is less than 0, the boson condenses, and via the Meissner effect, it sees this combination of capital A minus little a. It Higgses that out, and that leads to the notion that little a is equal to big A. And if you stick that in here, you get back the fractional quantum Hall state. Okay, so that's the two phases are encoded in this boson description via condensation. And so the condensate, the Higgs state of the boson, is the quantum Hall state. So we're thinking about Hall crystals. It doesn't take a leap of imagination to suppose that, therefore, the Hall crystal must be a supersolid phase of these bosons. And so much of what I'm going to tell you about can be thought of from this perspective and looking at supersolidity of the bosons. Okay, so it's a fairly obvious idea. And okay, so I have 20 minutes. Okay. So are there any questions? Feel free to interrupt if there's any questions. Okay. Yeah. Yes. So the supersolid phase has a finite superfluid stiffness, and it breaks translational symmetry. Well, you can start with an imposed lattice, and then it breaks the lattice symmetry further. That would be an example of a supersolid. Yes, that's the same. It's going to be the same. Yeah. Yeah. Okay. All right, so I'm going to start with the lattice, okay, and then I'll touch on the continuum. The basic setup is we'll have electrons in a strong magnetic field, and I'm going to impose some periodic potential. The amplitude of this periodic potential will be small compared to the cyclotron spacing, so that I can think of it as a perturbation. And I can think of the electrons as essentially the lowest Landau level. The Landau level will be broadened by the periodic potential. And the density in the lowest Landau level will be some function of the magnetic field and the chemical potential, which can independently be varied. And therefore, I can assume that I can tune independently the filling fraction, the fraction with respect to the Landau level states, and the filling with respect to the lattice independently. Now, if the filling with respect to the lattice were incommensurate, this would become a very complex problem. But I'm going to assume that the filling is a rational number so that any translational symmetry breaking would be discrete symmetry breaking. Okay. Right. So what I'm going to do is, suppose we have imposed a triangular periodic potential in the lowest Landau level as a perturbation. And I'm going to look at filling fraction such that the Hall conductance is 1 over 2 pi n, and n is an odd integer. So within this Chern-Simons Ginzburg-Landau theory, the bosons will see a net 0 external magnetic field. And let me further suppose that we don't have Coulomb interactions, but we have screened Coulomb interactions. Screened to the point where you just have nearest neighbor or on-site interactions and some nearest neighbor interactions. And if the on-site interactions were strong compared to the nearest neighbor, the bosons are effectively in the limit of being hardcore bosons. And as I said, they see no net magnetic field. Now, because the system is, these are not bosons, but these are so-called composite bosons, they couple to a Chern-Simons theory, they actually have unscreened, even though their Coulomb interactions are screened, there are unscreened current density interactions that come from the Chern-Simons term. Okay? So one way to see this is if you integrate out the Chern-Simons gauge field, you'll generate density-density screened density-density interactions, but unscreened current density interactions. For instance, this is an example where the density at x and the transverse current at y, that means perpendicular to the line between x and y, feels a 1/r potential. That's coming from the Chern-Simons interaction. So that's going to be the thing that changes, well, that could change the behavior of these bosons in this problem. And for the sake of simplicity, let's start with the case where the bosons are at filling fraction 1/2, okay, with respect to the lattice. Okay, so the electrons have this Hall conductance, and the bosons are at this filling with 0 flux. Now, in the hardcore boson limit, the effective Hamiltonian will have a kinetic energy for the bosons, and we can address the chemical potential. We can work with the grand canonical ensemble, although most of the calculations we've done thus far are in the canonical ensemble. There will be a nearest neighbor repulsive interaction, and then a density current interaction, whose coupling is in the inverse Hall conductance. So in the hardcore limit, the boson maps onto some spin system, where the creation operator of the boson is a S plus spin raising operator, and the density is the Z component. So in similar way, you could write down the current operator between I and J as just I times S plus S minus. And you can obtain all of these states can be solved in various limits, but ideally you'd like to solve this via, say, quantum Monte Carlo, but I think because of the current density interaction, there'll be a sign problem. And so what we did as a preliminary study of this was just to do mean field theory. Okay, so the analysis is just to treat the spins in this mean field solution as just classical vectors and on the block sphere, and you minimize over the spherical coordinate angles and find the phase diagram of the system. Okay, it's an uncontrolled expansion, but if you're in a phase of matter, you'll get the critical phenomena wrong. But if you're deep inside a phase, where the correlation length is short, it should work just fine. And in this approach, the density of bosons is related to the Z component of the spins. The superfluid fraction is the in-plane component, and the current is this operator here, which depends on both theta and phi. Yeah?
Just to understand, so you're taking the composite boson theory,
yes,
integrating out the Chern-Simons fields,
yeah,
and trying to regulate this on a lattice?
Yeah, exactly. Yeah. Which can be done. Okay. And okay, so what we find when we do this is for the filling fraction 1/2, we find robust supersolid order for these composite bosons. Okay, so when in units of the hopping of the boson, which I set to 1, there's a nearest neighbor potential V, which is in units of the hopping. For some value of the inverse Hall conductance, which I show here, you find that there's a phase diagram in which at small v, there's a superfluid phase. That would be the fractional quantum Hall state, fractional quantum Hall liquid. And then at larger nearest neighbor repulsion, you go into the supersolid phase. Okay? And now, what's the nature of this supersolid phase? You can see it here. We start with a triangular lattice. The system breaks the symmetry. This length here is square root of 3 times the distance between triangular lattice sites. So this is sometimes called the root 3 by root 3 order. And this is what I'm showing you here is the density. So there are 3 different sublattices with different densities. The sine theta here is the superfluid fraction, so the superfluid stiffness. It also varies spatially. So it's finite, but spatially varying. And then finally, an important requirement is that in addition to there being a charge modulation, there must be orbital currents in the supersolid phase for the bosons. And these are shown here. Now, just in case there are questions on this, let me explain why there must be orbital currents. So if you look at the equations of motion of the Chern-Simons-Ginsburg-Landau theory, you'll find that the flux of the little a is related to the density of bosons minus the external magnetic field. Okay? So, and in addition, the density of bosons is equal to the density of electrons, just from looking at the equations of motion. So if we had a uniform state where the electron density is this filling fraction times the external flux density, and this is equal to the boson density, you can see that the right-hand side is 0, and the bosons don't see a flux. By contrast, if there were a non-uniform state, as the supersolid is, if the density of bosons is some average density, which cancels the flux, plus a spatially varying part, then you can see that there's a flux which is also spatially varying, which is equal to the spatially varying part of the density. And so the bosons then will feel a non-zero flux, but there's no net flux because it's positive, negative, positive, negative. So a non-uniform state will always have some non-zero flux. And furthermore, from this observation, if you're in a supersolid, the spatially varying part can be expressed as a Fourier series over some discrete set of reciprocal lattice vectors, G. And from the flux or from the equations of motion, you can express the gauge field in terms of the spatially varying density. Okay? And since the current has both, by gauge invariance, a paramagnetic piece and a diamagnetic piece, the paramagnetic currents vanish in the supersolid, but the diamagnetic term is the gauge field itself times the density. And so that says that if you have a spatially varying density, from these expressions, you're going to have orbital currents that are staggered throughout the unit cell. So that's a property of this supersolid phase. Okay. In addition to this system at half filling, what I want to make is a couple of brief remarks. So the phase boundary that we found earlier between the superfluid and the supersolid was at some finite value of the current density interaction. And we found that the precise coupling of the current density interaction did not affect strongly the phase boundary between the superfluid and supersolid phase. We looked at other fillings. For instance, if the boson were on this lattice at some filling fraction, say 2/3, we did not find a supersolid phase. So this is reminiscent of older work done by, here's a paper by Kedar done way back in 2005, and also around the same time, people were looking at supersolids of ordinary bosons. You find that the critical coupling, well, so first of all, our results, even though we're doing mean field theory, somewhat remarkably agrees pretty well with the more exact solution of the quantum Monte Carlo of the system without current density interactions. And furthermore, people did quantum Monte Carlo at 2/3 filling, and they failed to find, so this is a superfluid, and this line here at 2/3 filling does not show supersolid order. And so that's also consistent with this simple mean field theory. Or rather, the mean field theory is consistent with this exact solution, exact numerical result. We also looked at the square lattice, and we found that just with nearest neighbor boson hopping, at least in the hardcore boson limit, there's no supersolid order. And importantly, also, the question about whether you get this with Coulomb interactions, unscreened Coulomb interactions, so far as what we've investigated, the supersolid order is far weaker with Coulomb interactions. What you seem to need is short range, not on-site, but finite range interactions in order to stabilize the supersolid phase. So the conclusion from this part of the analysis, if you wish to take home anything, is that the Hall crystal phases are most favored on a triangular lattice near half filling. It's a very robust supersolid phase of both bosons and composite bosons with screened Coulomb interactions. Okay, so what about the continuum limit in the last few minutes? Yeah. Okay, so if we go back to the Chern-Simons-Ginsburg-Landau theory, what I want to do is have a potential, a set of interactions that are not contact interactions, like you would have in usual superfluid. If we were talking about helium-4, you would have contact interactions, and that's the so-called Gross-Pitaevsky model. But here, with electrons, you could imagine non-contact interactions, some finite range, which I call U of r minus r prime. And for simplicity, let's just have it to be a step function. So some number U0 for short distances, and then falls off to 0 afterwards. So you can look deep inside the superfluid phase, or with composite bosons, deep inside the fractional quantum Hall phase in the continuum, and that's just Gross-Pitaevsky plus Chern-Simons. Okay, so we have Gross-Pitaevsky equation with some non-local potential, supplemented by the equations of motion for the currents. That's the Chern-Simons. And one simple way to solve this is to do Bogoliubov theory. By that, I mean you go deep inside the superfluid phase of the boson, you assume some amplitude and a phase, and you integrate out the amplitude fluctuations, and you get an effective theory for just the phase modes. And that's another way of restating what Bogoliubov did. So in Bogoliubov theory, you get a linear phonon spectrum at long wavelength, and then a quadratic dispersion beyond that with contact interactions. If you make the interactions like this in a superfluid, you can get a roton. The difference in our case is that there's no phonons here, as also we heard this morning. Because of the Higgs mechanism in the language of the Chern-Simons-Ginsburg-Landau theory, the phonons are pushed up to finite energy, and that energy comes out to be the right energy, known as Cohn's theorem, B external over M. And what you find is that, yes, there are rotons, but what I'm afraid what you find from this analysis is that the interactions required for the roton to go soft, and if they do go soft, you will find a triangular lattice. The interaction required is very strong, and I wouldn't trust the Bogoliubov theory in the limit when the interactions are, these are in units of h bar over 2m times the a squared. Okay? So in that limit, I would not trust the Bogoliubov theory, but this is indicating that it's possible to get a Hall crystal from the continuum. It's just much harder than it is by getting it directly on the lattice. Okay, so I think I'll stop here. I talked about Hall crystals from the Chern-Simons-Ginsburg-Landau theory, and the obvious description of that is in terms of a supersolid of composite bosons. The Hall crystal are much more likely to be observed with weak periodic potential than in the continuum, which is at least qualitatively consistent with the fact that we see them in these anomalous versions of the fractional quantum Hall states where there is a lattice, but we don't, to my knowledge, have never observed the Hall crystal in the 2D electron gas in the say, gallium arsenide. One final comment I'll make is that if you did go from the continuum to a crystallization, it's not clear from, Bogoliubov theory would say you get a supersolid, but you might also get a Wigner crystal. And so there's the possibility of a direct Wigner crystal to Hall crystal transition. And that, within this Chern-Simons-Ginsburg-Landau theory, would be governed by the Wilson-Fisher fixed point plus Chern-Simons terms. So for instance, for the integer quantum Hall crystal to the Wigner crystal, that's Wilson-Fisher with level 1 Chern-Simons, and that's dual to a free fermion. So we presumably understand that theory very well. But in the fractional quantum Hall state, to my knowledge, we don't know what that is, and that requires further investigation. So I'll stop here. I'm done with my talk. Thank you. Take questions.
Well, are you saying that the fractional chain insulator? Are you saying that the fractional chain insulator is the Hall crystals?
In certain cases, in the fractional cases, I can't say that. So
what are you saying?
The integer quantum Hall state at filling with the lattice of 2/3 is a Hall crystal.
In what system? Sorry.
Okay, so let me go back. This was in graphene.
In graphene.
Yeah, in pentalayer graphene. So because I'll explain why.
Which is a fractional Chinese, supposed to be a fractional Chinese sleeve.
Yeah. So, okay, so in that
So
case,
this is a theory of,
this is, yes, yes. This,
so the statement is that.
No, I'm not saying that. I'm saying that this is an effective theory, and it would govern a Hall crystal that if it exists. Now, I think you're asking a much higher level question about reality, and are these systems, if I understood you correctly, are they really Hall crystals? Let me just back up manually. Let's see. Yeah. So what I'm saying is, so this is graphite, pentalayer graphene, okay? This system, for instance, look at this line here, which the experimentalists identify as an integer quantum Hall state. Sigma xy is -1, but the density is 2/3 with respect to the crystal. So if it's a gapped state, with a non-degenerate ground state, like the integer quantum Hall state is, there must be an integer number of particles per unit cell. Okay, so this filling fraction 2/3 is not an integer. So if you want to have an integer, you must reconstruct the unit cell, double or triple the unit cell in this case.
So you're trying to explain an integer quantum Hall effect of the electron densities, which if it was a regular, it would be a fraction of the.
Yeah.
So what does the supersolid aspect? I mean, what are the properties?
The supersolid has, well, so first of all, you mean in the composite, in the Chern-Simons-Ginsburg-Landau theory, or? Yeah, so it's got no low energy modes. Okay, so there's no phonons. I mean, there are phonons if you allow the crystal to. It has a superfluid stiffness, so yeah, it does flow. Yeah. So yeah, there's the non-classical rotational inertia. It would exhibit that phenomena, for instance. Yeah, that's right. Yeah.
We can have more questions. We'll have 2 or 3 minutes.
Hall crystal with the continuum limit. So how do I define the filling fractions in those cases? Because if there is no crystalline...
You could ask the same thing about a Wigner crystal, right? What determines... So if you're in the continuum limit, you have strong Coulomb interactions.
But there at least magnetic field is there. So I know Landau level, I know what is the filling fractions.
Yeah.
But
yeah, same here. The Hall crystal in the continuum, if you have a quantized Hall effect in the continuum, it requires a magnetic field, right?
So your reference is filling, for example, E square over A is that filling is, you are saying that's my reference? Like what I'm saying is this, pentalayer, I have this moire.
Yeah.
I know the real space.
Yes.
So I know the filling fraction I can define.
Yes.
That's a weak periodic potential.
Yes.
But when you continuum,
yeah.
How do I define?
So then, okay, so that's what I was trying to say actually. So this, whoops, okay, I can't find it now. The electron density is, it's a thermodynamic property. It depends on field and chemical potential independently. So you can tune it either way. So if you're in the continuum and you don't have disorder, the Landau levels are sharp, then the only way to define it is the filling fraction with respect to the Landau level, the number of electrons divided by the number of flux quanta. But if you're on a lattice, you have a lattice filling and the Landau level filling fraction, which determines the Hall conductance.
I'm saying for this experiment, there's no magnetic field.
Correct, but there's a crystal, so the only filling is the filling with respect to the lattice. Yes.
So naively, it seems like the Hall conductance does not change as you go through the transition to the quantum Hall crystal.
You mean from the quantum Hall liquid to the Hall crystal? That's correct. It's a first order transition, like in crystallization, if you go into a triangular lattice. Within Chern-Simons-Ginsburg-Landau theory, there's a cubic invariant that you generate, and so there will be a first order transition. But the Hall conductance doesn't change, that's correct.
But you're saying I shouldn't think of this as like a Hall system stacked on top of something undergoing a translation symmetry breaking transition.
Sorry, I don't understand.
If I have a quantum Hall system just stacked on top of
a periodic potential,
something that's undergoing a gas to...
Well, so if you've explicitly broken translational symmetry, then you can break translations further, which is what I was talking about. So you could go from a lattice translational symmetric quantum Hall state to one that further breaks the lattice transitions to, say, double the unit cell or something like that. And that would preserve the Hall conductance. That's the closest I think you can have to what you have in mind. But if you simply impose a periodic potential, there's just a crossover, right? There's no phase transition. Okay.
We have time for one more question. So, I hope I didn't miss the answer to this question during your talk. So, how would you distinguish this from an actual crystal of quasi-particles? I think.
Yeah. I didn't mention that in this talk. So, within the superfluid or superconducting description of the quantum Hall effect, we also know that if you go away from the filling fraction, the bosons will see a net magnetic field. And then you generate a vortex lattice. This is the Abrikosov vortex lattice problem of the bosons. That would be the pinned quasi-Hole or quasi-electron degree of freedom. And by Bert Halperin's notation, that's called a partial Hall crystal because the density of quasi-holes can smoothly vary by changing the magnetic field. Like in a vortices in a superconductor, if you add more and more field, you add more and more vortices and they pack closer and closer. So it's compressible with respect to the density of vortices.
One more question.
Yeah, whereas the Hall crystal is not. If you want to add additional charge, it's a gapped excitation. Yeah. Okay.
Are there any further questions? Okay, if not, then let's thank Sri again.